All right, it's 4:45. I think it's time to get started. I'm Mike Danese. I'm going to give a talk about caller ID and Kubernetes today. A little bit more about me. I'm a software engineer working on GKE for the past 4 years. Currently the TL of GKE Identity, and I'm also active in the Kubernetes Special Interest Group for authentication and authorization. So the first topic I wanted to touch on is user data. It plays a crucial role in many amazing applications that provide tremendous value to customers. However, when a user hands over data to a company, they do so with an expectation of privacy and expectations on how that data will be accessed. And as application developers, it is our responsibility to uphold those expectations. Which brings us to the problem that I want to cover in this talk. So how can we create an environment that maintains a sufficiently high level of assurance on user data? So what is sufficient here? What is assurance? This is far too vague to be turned into a feature request. However, to better understand this problem, I would like to go through a game of telephone between services running on Kubernetes. We'll add some requirements along the way in the spirit of better protecting user data, and we'll see how those requirements can be met with solutions built into and on top of Kubernetes. But before we get into our game of telephone, I wanted to cover just a couple concepts that I'm going to refer to throughout this talk. The first distinction that I want to make between coarse-grained authorization and fine-grained authorization. So coarse-grained authorization is a broad privilege independent of the object targeted by the request. So you can think of a coarse-grained authorization as permission to call the getBook RPC. And fine-grained authorization is narrow privilege specific to the object targeted by the request. So fine-grained authorization would be you can get book Noah's Ark, or if that was a book. Cool. The second distinction that I want to make is around credentials. I'm going to talk about channel-bound credentials, which are bound to the channel that they're received on. TLS is an example of a channel-bound credential where it's bound, where the channel is the TCP connection that the TLS session is established on. And then on the flip side, there are forwardable credentials, which are credentials that are not bound to the channel in which they arrive on. So an example of this is a bearer token. You can send a bearer token down a TCP connection, close that connection, and open another one, send the bearer token down it again. We call these forwardable credentials because the person that you send it to can turn around and forward it to another party if that other party accepts that same bearer token. And the last thing that I want to discuss before we hop into our game is direct authentication versus delegated authentication. So direct authentication happens when a server authenticates the proximate or adjacent requester or the peer. Delegated authentication happens when a server authenticates a requester not by the direct requester, but by the originator of the request. So an example of a delegated authentication would occur if a backend authenticates an end user that made a request that traversed through a front end. So that's a delegated authentication. So now with that background, we went through that rather quick, but hopefully as we go through our scenario, some of these concepts will be clearer with examples. So let's hop into our game of telephone. I want to introduce backend. It sits inside a secure production network. It has a lot of interesting sensitive data, but it's not very interesting when it's all by itself. So if we zoom out a little bit, we'll see that it lives alongside a couple other services. We have a service front end, which is responsible for serving the front end of my application. And we have a widget service, which is responsible for serving widgets. And so far, the front end and the widget service can communicate freely with the back end. We write this all down in the design doc and submit this design doc to our security team for review. And they come back to us and say, hey, widget service really has no reason to be able to talk to backend. Backend holds a lot of sensitive data, and widget doesn't need access to any of it in order to perform its function. So enter the first requirement of this talk. The security team asks us to grant permission to call backend only to our front end. So this is an example of a coarse-grained authorization rule. We think that a possible avenue for implementing this feature request is to implement some form of caller ID within our service stack. So let's embark down that journey. As it turns out, Kubernetes has a built-in concept of a service account, of a service identity. Kubernetes service accounts are a resource type. They live in a namespace, and each namespace has a default service account. All pods are already running as a service account. They integrate with access control. They can be the subject of an RBAC policy or a pod security policy. And probably the most important thing to us is that they have automated credential management to an extent. So let's dive into that last bullet a little further to see how it can address our problem. So the tokens are the built-in credentials provided to services, to service accounts. They are exposed to pods via kubelet volume. They are flexibly verifiable. They can be verified either centrally by communicating to the token review API or by distributing a verification key, and you can do a standard JOT verification against these tokens. They are revocable via the API to an extent, and then the last three bullets are true of the new style service account tokens that are beta in 1.12 Kubernetes. They have limited TTL with automatic rotation, and they support audience scoping, and they're never stored in etcd. So they have a lot of good security properties that make them seem like they might be useful for our use case. There's quite a complicated flow that goes into making these tokens available. That starts on pod creation. The kubelet will request a token from the API server, and it will continue to request tokens to from the API server throughout the lifetime of the pod in order to make sure that those are refreshed. It's a pretty complex diagram. I'm not going to step through it because most of this is handled by the infrastructure. And what you really have to care about is your front end and your back end. So your front end reads a token from disk, presents it to your back end, and back end authenticates that token, and possibly returns a response based on the policy, enforcement policy. However, there is a major downside to this approach. So tokens are an example of a forwardable credential, so they may be replayed. What this means is that you actually have to be very careful with who you send these tokens to. The other thing that we haven't solved is server authentication. When front end dials back end, it wants to be fairly certain that it's talking to back end and not something else. We would rather not have to trust the network for security properties like this. The way that you traditionally do this is with server TLS certificates. But we're in kind of a pickle. We need to be careful with who we send these tokens to, but we are unable to authenticate servers. So this seems like it's going to be incompatible with our requirements. So if we move forward a little bit, we can also provision mutual TLS certificates for service accounts. These are awesome because they provide both server authentication and they are channel bound, meaning we don't have to worry about these credentials being replayed. Kubernetes does have support for a certificate provisioning via the Certificates API. It's very flexible, but it requires, I would say, substantial integration to get working for your use case. There is another equally complex flow that starts with the front end submitting a certificate signing request to the API. An approver, which you have to write, observes that CSR and does some authorization check and approves it. A signer separately signs that into a certificate. Front end reads the certificate and can now use that to establish a mutual TLS channel between front end and back end. And of course, back end also has to do the same flow in order for it to get its serving certificates. So there's not an easy way to get to this where we're only worrying about the same thing. We're only worrying about the things that we care about. However, if we do introduce Istio, it actually provides a lot of the heavy lifting for you. So Istio has a component called Citadel, which is the CA component. It provides an API to exchange a Kubernetes service account token for an MTLS certificate. The Istio node agent actually automatically does all this for you and exposes those TLS secrets to your pod automatically. So if we do decide to adopt Istio, we get back to the picture that we like, where we're only worried about the things that we care about. Front end has a certificate, it presents it to back end, mutual authentication is established, and the response is returned. So this sounds pretty good for now. Let's apply it. Let's apply this to our game of telephone. So armed with mutual TLS to secure service-to-service communication, we can implement some enforcement policy in the back end that says the front end identity is allowed to call back end, but the widget service is not. And this looks pretty good. The security team is happy with this, and we can move on. However, we were still a little bit too narrowly focused. We're still focused only on our internal network. And as we zoom out, we notice that not everything is contained inside our internal network. We actually have a gateway, which is the conduit between users and our services. This is awesome because it means that the front end and the widget service and the back end can provide value to customers outside of a prod network. However, it does create some new challenges. The security team zoomed out a little bit too, and they gave us a new feature requirement. This new feature requirement is slightly different than the first one. They want to model our authorization policy such that only user A can access user A's data. So this is an example of a fine-grained authorization policy. But this presents a little bit of an issue because user A talks to the gateway where user A is authenticated, and the attributes that come out of that authentication actually have to are the input to the policy of the backend. So we have to figure out how to transport those attributes all the way to the backend. This is an example of a delegated authentication problem. However, Istio Will is currently working on a solution for you. Istio is developing this concept of a request context token. It's all designed. Implementation is ongoing. It is pre-alpha, so it's not something that you can use when you leave, but I'd like to describe some of the theory behind it to you today. The idea is that this request context token captures request context at ingress, packages it in a JOT so that it can be sent downstream and validated, and it supports attributes like source IP, but it also supports identity attributes like end user identity or request originator. And that last attribute is the one that we really care about here. So to dig into how this actually works, the user sends potentially a bearer token or some other form of end user authentication to the gateway. Gateway sends that bearer token and some request context to the token service. Token service returns an RC token. Gateway passes that RC token in a side channel down the service call stack. In an out-of-bound channel, an RC token verification key is pushed to all applications running in the cluster so that they can verify those incoming RC tokens and trust that those assertions were made by the gateway and the token service. So if we hop back to our game of telephone, we now have a user authenticates to the gateway creates an RC token. Those RC tokens are forwarded upstream, and backend is able to validate that RC token and use those attributes to feed its policy. So now we can implement the policy that user A has permission to access user A's data. However, we actually have a little bit of a regression with this change. Suppose widget service gets a remote code execution. Those RC tokens are passed down to upstreams indiscriminately. So widgets in RCE and widget service would have access to the same RC token and could forward that to backend to gain access to sensitive data. So potentially we were overzealous with our shift, and what we really wanted to do is simultaneously enforce that coarse-grained authorization policy and the fine-grained authorization policy. So we grant access to front end to call back end, and we grant access to user A to read user A's data. And what we get is a picture that looks like this. This is pretty good. This feels like where our security team wants to be. I want to dig into that final authorization policy that we had in the last slide and rephrase it a little bit. So a rephrasing of that is with proof of recent interaction with user A, the front end can access user A's data. So we've created an explicit requirement that the access to user A's data is always on behalf of user A. In this specific scenario, we're actually requiring that the access taken on behalf of the user must be in response to a recent action taken by the user. And we're also requiring that the accessor, the direct accessor, proves that this interaction occurred. So we've basically remodeled our access management story around the idea that the user owns their own data. But furthermore, using those coarse-grained authorization policies, we've constrained how the powerful user authority can flow through our system, and we've restricted the paths to the paths required for us to fulfill business requirements. So the feature creep never ends. You may want to restrict service calls by that originated in your prod VPC, you may want to restrict service requests based on code identity of the service. We didn't talk about this persona at all, but there is also an administrative persona. Maybe the administrative persona does not need proof of user interaction to read, to access user A's data. Maybe justification in the form of a support ticket or a bug ID is sufficient. And you also might want to require that administrative requests originate on company-issued devices. We don't have time to go into how all these different authorization policies could be implemented, but we do have the groundwork and the extension points where we could start to build, where we could start to expose attributes like these to policy. Another side effect of this approach is now if we record the who, what, when, and why all these accesses occurred, we can, with the improvements that we made of our in our authorization system, the context of why these accesses occurred are actually much more meaningful and significant and actionable. It's incredibly useful when you need to do forensics to figure out why something happened when things go south. So our talk began as a talk about responsibility, and you can't have responsibility without accountability. This is the sudoers lecture, respect the privacy of users, think before you type, and with great power comes great responsibility. The reshift of this authorization model to include both fine-grained authorization that takes into account the user, and also coarse-grained authorization to control the flow of user authority through our system, actually has actually moves the responsibility of data protection onto individual SREs, service owners, administrators. As these teams develop code or debug problems in production, they make decisions that are conscious of the privacy of users. So I think that potentially the thesis of this talk is that by implementing these controls, we are actually moving the idea of user data protection into a shared ownership or shared responsibility rather than a responsibility of another team, and that helps push it towards a core principle of a company or engineering team. So how did we do with our original problem? Did we solve it with authentication? The bad news is probably not. It's a pretty complex problem. It requires a holistic approach and sustained diligence, and you're never going to have a perfect solution. However, we did lay the foundations for this holistic approach by allowing granular authorization, which enables least privilege access, and a complete audit history, which builds an environment of accountability within an organization. In closing, I wanted to talk about what I look at when I evaluate solutions in the space. I like to see solutions that are easy to adopt, hard to use incorrectly, and noisy to circumvent. applied consistently across the infrastructure. This usually means that it is a core service provided by the infrastructure, built on open standards, and easy to develop and extend. So the other thing that I wanted to touch on is what belongs in Kubernetes core, and probably not a lot of this right now. We want to build extension points that allow experimentation outside of core. We also do want to adopt features that improve and harden our core infrastructure. We have to actually move very cautiously because anything that we incorporate into core Kubernetes will be stuck with for a long time, including any mistakes. So that brings us to the call to action. What can you do when you leave this room? Continue thinking about this problem. Start from the basics. This isn't going to happen overnight. If you don't have service identity, it's a great spot to start. If you decide that you want to embark down this path, please give us plenty of feedback of what works well and what doesn't work, and what we could do better. I also want to point out that there are a few communities that are doing great work in the space. SIGAuth, which I am involved in. Spiffy and Spire are building great identity solutions, and the Istio security working group developed many of the features that I discussed today, built on top of Kubernetes, and they're working hard to build a platform that integrates very smoothly with Kubernetes. And that's it, and I think we have some time for questions. Any questions? Don't be shy.
Do some of the older solutions, I'm thinking Kerberos and SAML, have a place in a cloud-native world?
I think that it's going to be a requirement to support these in some capacity, especially not every application is going to be greenfield. We need to have support for migrating. So we talked about a gateway. Kerberos is often used for administrator identity. That gateway should probably be able to authenticate using Kerberos and support AD. For Kerberos to services, for Kerberos for service identity, I think that's less of a clear space for me, but I think that it is important. We're just looking for users and use cases that need that, and people that are motivated to start to sketch out what a solution would look like. We're happy to build in the extension points that are needed for that and explore it. We just don't have the motivation yet. Anybody else?
It's a nice idea to build things up layer by layer. Have you compiled a sort of a matrix of that feature creep use cases list, which build up layer by layer, to show what solutions can be applied at each layer, so you could from that derive your security architecture that fits your particular needs, and it would probably help a lot of people to start and see which layers combine, which are orthogonal to each other and stuff like that.
Right. Yeah, I think that there were, naively, I could probably categorize 3 without thinking about it. There was the layer where we could only authenticate to the Kubernetes control plane to get certificates, because we could only trust the Kubernetes control plane. And there was when we established service to service identity. And then there was the layer where we started to plumb the end user or request originator identity through the system. And that could, I tried as best I could to expose those, but maybe a blog post or something along the line would be able to fill in all those details. So it's a good recommendation. Thank you.
Yeah, so in the description for the lecture, you wrote something about the newly released proof of pod identity. Did you refer to the service accounts or something new? If you can elaborate on that a little bit.
Maybe I didn't call that out. The new proof of identity was the service count token. So in 1.12, there's two new features called the token projection, which most of the security properties that were improved were actually properties of only the new service count token. So those are automatic rotation, time bounding, and also audience bounding, and they're not stored in etcd, so they don't depend on secret mechanisms. So I should have called out that was the improvement, but yeah, these slides are up online, so you can read about that.
Great, thanks.
Sure.
Can you talk a little bit about the token service? I guess you have to exchange the bearer token to something like Istio understand. Is that like extensible?
It is. It supports arbitrary attributes that can be asserted by the gateway. It is extensible in that it will support different identity providers. It is currently spec'd to be a JOT that is verifiable using the token services verification key.
So the gateway is responsible for verifying bearer token is a valid like user cookie.
Yeah, so the gateway is responsible for verifying that the token is a valid user cookie. The gateway, the system of the token service and the gateway. So the token service is actually, the gateway, for example, sends headers and source IP to the gateway, and the gateway does, the gateway sends headers and source IP and some other ambient request attributes to the token service. The token service performs authentication and builds a JOT containing the request context that can be then forwarded downstream and authenticated by downstream services or upstream. It is extensible to arbitrary attributes and hopefully arbitrary identity providers.
Hi, my background is I am not Kubernetes. I'm here trying to learn, so I don't totally understand the use case, but it sounds like this is some permeation of a two-legged OAuth solution. Did you guys look at OAuth and the spec and sort of validate the use case against that?
So it could be, you could use OAuth coming into the gateway. However, the RC token is not a bearer token. It is less powerful because it can only be presented by specific peers. So that was the idea that you control the flow of the RC token through the system. So they're not actually usable generally like a bearer token is. So a bearer token is defined as something that any client can use without proof, cryptographic proof. Does that make sense?
Yeah, I'd like to discuss it.
Yeah, absolutely. The idea is that RC token is actually much less powerful than the end user bearer token, which is the motivation for exchanging it. Because we do control the paths that it flows through the system. But happy to talk about it after. Anybody else? One more. Thank you.
Yeah, I just have a question. I heard about it, but I'm not sure if you can elaborate on it. Process identity, like distinguishing between the actual stuff that runs on the pod versus somebody running kubectl exec on it, giving it different access based on like, I don't know, bits or some kernel attributes.
That is a hard question. And it is not going to be covered by this talk, although there is ongoing work in the Linux audit subsystem to build out container ID hashes on processes, so you can actually distinguish between processes based on a container ID. That was probably not covered in this talk, and it is not in the mainline Linux kernel, but eventually there could be some integration here with workload identity and the container ID of a process.
Is this something you guys are still working on? Is it,
it's something that teams at Google are working on integrating, but those teams are actually pretty far away from where I sit. But once it's ready, happy to figure out how to integrate with it. Anybody else? Thank you, everyone.